Here's the next exercise, which involves performing a finite element FE analysis on a plate made of 2024 T3 material. The given plate has dimensions 100 mm into 40 mm into 3 mm, and it is subjected to a 40 kilonewtons tensile load in the x direction. The goal is to evaluate elongation, strain, and stress in the plate under the applied load. This slide provides an overview of the 6 major steps involved in conducting a finite element analysis, modeling of geometry, creating the digital model of the plate. Creation of mesh, dividing the model into small elements for analysis. Material and element properties, assigning material properties to the elements. Loads and boundary conditions, applying forces and fixing constraints. Solution, running the simulation to compute results. Post-processing and validation, interpreting the results and verifying their accuracy. Understanding each step in detail is crucial to ensure accurate simulation results. Modeling the required geometry is the first step in finite element analysis. The plate geometry must be accurately modeled in CAD software or directly in the FE software. In this exercise, FreeCAD is used to model the geometry. FreeCAD is an open-source tool that allows easy parametric modeling. The image represents the interface of FreeCAD, where the plate is being modeled. In FreeCAD, the navigation style can be selected from the bottom right corner of the interface, where different navigation options are available. This allows users to switch to other styles like Blender, CAD, and Touchpad as per their preference. These are the shortcuts shown in the image for the Blender navigation style. Ensure the FreeCAD workbench is set to part design before starting the model to access the essential tools for creating and modifying parametric models. Click on the Create Sketch button. Alternatively, you can find this option in the Part Design menu. Selecting this option prompts the user to choose a reference plane for the sketch. After clicking Create Sketch, FreeCAD asks you to choose a plane on which to draw the sketch. The available planes are XY plane, XZ plane, YZ plane. These planes represent the fundamental coordinate system in FreeCAD, allowing you to start drawing in 2D before converting it into a 3D shape. In our case, we choose XY plane. Once a plane is selected, FreeCAD switches to sketch mode, allowing users to draw shapes like rectangles, circles, or lines. This slide is a continuation of the previous step in FreeCAD's Part Design workbench, focusing on sketch creation, adding constraints, and achieving a fully constrained sketch. In the Sketcher workbench, after selecting a plane, you need to create a basic shape. The Centered Rectangle tool is selected, highlighted in red. This tool allows you to draw a rectangle centered at the origin. This is useful for symmetrical designs as it automatically places constraints on the rectangle. The center point of the rectangle is placed at the origin, 0, 0. The initial sketch appears, but it is not yet fully constrained. This means that FreeCAD does not have enough information to lock the shape's size and position completely. Constraints are used to define the shape mathematically. In the image, horizontal length 100 millimeters and vertical height 40 millimeters constraints are typed in. The lines turn green, indicating that the geometry is now constrained. In the left top section, the Solver Messages panel shows fully constrained, meaning the rectangle's position and dimensions are completely defined. Once the sketch is fully constrained, you can click Close to exit the sketcher. We will continue with the first step of geometry by creating a ruled surface in FreeCAD, which is useful in surface modeling. The Ruled Surface tool is selected from the Part Workbench toolbar. This tool is used to create a surface between 2 edges or wireframes. The selected edges or wires, green lines, from the previous sketch are used to generate the surface. The ruled surface is created between these edges. You may have to unselect all the edges if selected earlier and choose only 2 parallel edges and then create a ruled surface. In the Labels and Attributes panel, a new entity ruled surface appears under the body. This confirms that the ruled surface is successfully generated and listed in the model tree. Now let us export the ruled surface as a step file for further use in other CAD software or simulations. Navigate to the File menu. Click on Export. This opens the Save As dialog box. The step file format is widely used in CAD software for 3D model exchange. Click Save to export the file. The model is now ready to be shared or imported into another CAD system. Now we will start out FE analysis by first importing the previously exported step file into PrePoMax. PrePoMax has limited geometry modeling options, hence we use FreeCAD for our geometry creation and edits. The image represents the interface of PrePoMax. In PrePoMax, you can navigate the model using mouse and keyboard shortcuts similar to FreeCAD. To pan, move the model, hold Shift middle mouse button, while zooming can be done using Control mouse scroll wheel. To rotate the model, you can either hold the middle mouse button or use the keyboard arrow keys. The process begins by navigating to the File menu located at the top left corner of the interface. From the drop-down options, select New to initiate a new analysis session. This triggers the appearance of the Model Properties dialog box, which is where foundational model settings are defined. In this case, 3D modal space is selected and the unit system type, which defines the primary units used throughout the model. The option highlighted in this example is mm, ton, s degree cells, which sets millimeters for length, tons for mass, seconds for time, and degrees Celsius for temperature. This setup ensures consistent unit usage across geometry, materials, boundary conditions, and results interpretation. Once all selections are made, we confirm the settings by clicking OK. Here the next step is to importing the geometry, which is the starting point for setting up an FEA model. The image outlines two ways to import a geometry file. The first method involves navigating to the File menu and selecting Import, or using the shortcut Control-I. This opens a dialog box where you can browse for and select your model file, typically in STEP, IGES file formats. The second method is quicker and uses the Import File icon found on the toolbar, highlighted in the left corner. Once the geometry is successfully imported, it appears in the model tree under the Parts section, as shown in the image. Here, the part is listed as Shell Part 1, indicating that a shell-type structure has been recognized, and it's ready for meshing and further setup. In this step, we define and generate the finite element mesh for the imported geometry. Meshing is essential for running finite element analysis, FEA, as it divides the geometry into smaller elements for numerical simulation. Go to the Mesh tab and click on Mesh Setup Item, then Create. This opens the Edit Mesh Setup Item dialog box. The first step is to define the mesh properties by selecting the meshing parameters type as highlighted in the interface. Here we define the mesh size by specifying the maximum and minimum element sizes, the number of elements per edge, and the number of elements per curvature based on the requirements of our analysis. After defining the mesh properties, click OK. Then repeat the process by going to the Mesh tab, selecting Mesh Setup Item, and choosing Create. This time, select the Shell G mesh type to define the shell meshing parameters for the model. Here, the mesh type is set to quasi-structured quad, which generates a grid-like pattern suitable for shell elements. Before proceeding to generate the mesh, you can click the eye icon to preview the mesh layout. Once satisfied with the preview, click OK to confirm the settings. The final mesh is generated by selecting Create Mesh from the Mesh drop-down menu. The software then processes the part geometry and displays the completed mesh in the viewport. The final mesh appears as a uniform quadrilateral pattern distributed across the plate geometry. With this, the meshing stage is complete, and the model is now ready for defining materials, applying boundary conditions, and setting up loads in the subsequent steps of the analysis. Here's a continuation of Step 2 Mesh, where we focus on creating node sets to support the application of boundary conditions and loads in later stages of the analysis. To proceed with the finite element setup in PrePoMax, we need to define node sets at specific locations on the model. These node sets act as reference groups of nodes and will be used to apply constraints, loads, or join to reference points. It's important to note that each FEA software handles these steps slightly differently, and what you're seeing here is specific to PrePoMax. In this example, two node sets are created, one named Fixed for the constrained edge, and another named Load for the edge where the force will be applied. Here we select nodes on the mesh using the Set Selection panel, choosing geometry-based selection such as surfaces or edges, then defines the name for each node set in the Edit Node Set dialog. The number of selected nodes, the center of gravity, and bounding box values are automatically displayed. After naming each set appropriately, clicking OK confirms their creation. On the visual display, the selected node regions are highlighted in red, clearly indicating the edges of the plate where boundary conditions and loads will later be applied. These node sets become essential references for constraints, like fixed supports and force applications, enabling precise and organized control over the model behavior in the simulation. In this step 2C, create reference point, we define a control point that will be used later to apply loads or constraints to a region of the model. Reference points are abstract entities that don't belong to the mesh but are used to simplify interactions such as applying loads uniformly over a node set. In this step, a reference point named reference point 1 is created using the bounding box center of the load node set, which was previously defined in step 2B. The region type is set to node set name, and the node set selected is load. This ensures that the reference point is spatially aligned with the center of that node group. The coordinates are automatically populated, placing the point at x is equal to 100 millimeters, y is equal to 20 millimeters, and z is equal to 0 millimeters, which corresponds to the far right edge of the plate where the load will be applied. These coordinates are based on the selected node set and cannot be manually edited. As shown in the right portion of the image, the reference point appears as a labeled dot, reference point 1, just outside the edge of the mesh, visually confirming its correct placement. Once this setup is complete, clicking OK finalizes the creation. This reference point will play a key role in defining a rigid body constraint and applying the external force during the loading step in the simulation. In this step 2D, create constraints, we define a rigid body constraint that links a region of the model to the previously created reference point. This is a crucial step that enables the load to be applied at a single point while distributing its effect over a selected surface or edge. In the PrePoMax interface, under the Constraints section, create a new constraint and sets the type to rigid body, as shown in the highlighted dialog box. Under the control point property, the reference point 1 is selected. This point was defined in the previous step using the center of the load node set. Under the region, the node set name for load is selected. Once confirmed, clicking OK finalizes the setup. Visually, the model now shows reference point 1 at the far right edge of the mesh, clearly indicating the location where the force will be introduced. This rigid body constraint ensures that all nodes on the selected region move together as a single rigid group, controlled by the reference point. It's a common and efficient method to apply point loads or motions in shell and plate structures while avoiding stress singularities or unrealistic local effects. Let us move on to step 3A, material property definition, where we assign material characteristics to the model to ensure accurate structural behavior during analysis. This step is performed within the Materials section, where a new material entry is created and named, in this case, Material 1. In the Edit Material window, select Elasticity from the list of available material models, which enables the definition of linear elastic properties. The elastic model is then added to the selected column using the arrow button. Once added, the user specifies the two key parameters required for elastic material behavior, Young's modulus and Poisson's ratio. In this example, the material is a aluminium 2024 T3 alloy. The Young's modulus is set to 72,390 megapascals, representing the stiffness of the material, and Poisson's ratio is entered as 0.33, indicating the material's lateral contraction relative to longitudinal extension. Once the material properties are defined, clicking OK finalizes the setup. On the right side of the interface, the material will later be assigned to the section of the geometry. In step 3B, create section, we assign the material defined earlier to the actual geometry by creating a shell section. In PrePoMax, this is done under the sections category of the model tree. Create a new section and selects the shell section type, which is suitable for thin-walled structures like plates and panels. In the Edit Section dialog, the section is given a name, example, Shell Section 1, and the material is linked by selecting Material 1, which was defined in Step 3A. The thickness is set to 3 millimeters, matching the actual plate dimensions. The offset is kept at 0, meaning the shell mid-surface aligns with the geometry surface. For the region, select the entire surface of the shell part using the Set Selection panel, which supports geometry-based picking. As shown in the image, the full plate is highlighted in red, confirming the region to which the section properties will apply. Clicking OK finalizes the section definition. In this Step 4A, Create Static Step, we define the loading scenario under which the analysis will be performed. In PrePoMax, this is done by creating a new step under the Steps section of the model tree. Create a new step by selecting Steps section. In the Create Step dialog box, the step type is selected as Static Step, which is suitable for problems where loads are applied slowly and inertia effects can be neglected, ideal for structural simulations like the one in this exercise. Once the setup is complete, clicking OK adds the step to the model tree. In Step 4B, History Output, we define the specific result quantities that we want the solver to record at each increment during the analysis. These are known as history outputs and are useful for monitoring forces, displacements, or other variables over time. In this example, we are creating a node output under the History Outputs section of the analysis step. A new output item named NHOutput1 is created, and under Variables to Output, the variable RF is selected, which stands for reaction force. This allows us to track the support reactions at constrained locations. Under the Region section, the region type is set to Node Set Name, and the specific node set chosen is Fixed, which corresponds to the left edge of the plate where the boundary condition is applied. Additionally, the Global and Totals options are left on default settings. After confirming all selections, clicking OK adds the output definition to the model tree. On the right side of the interface, we see the selected node set highlighted in red, visually confirming that the history output is applied to the correct region. This step is essential for validating the model, especially when checking equilibrium or comparing calculated reaction forces with the applied loads. In this Step 4C, Create Boundary Conditions, we define the constraints that restrict movement in the model, essential for ensuring the simulation reflects real-world physical support. In this example, we apply a fixed boundary condition to one edge of the plate, using the node set created earlier named Fixed. From the BC's Boundary Conditions section under the Analysis step, we create a new boundary condition and set the type to Fixed, which fully constrains all translational and rotational degrees of freedom. In the Edit Boundary Condition dialog box under the Region section, the region type is specified as Node Set Name, and the appropriate node set is selected as Fixed. This links the constraint to the nodes along the left edge of the plate, which are visually highlighted in red in the model view. Once these selections are made, clicking OK finalizes the boundary condition setup. This constraint ensures that the left edge of the plate remains stationary during the analysis, allowing us to observe realistic deformation and stress responses on the rest of the model when loads are applied. In this final part of Step 4, we apply the external force that will be used to simulate the loading condition on the structure. In this case, a concentrated force is applied through a reference point, which allows the load to be evenly distributed over the selected surface via the rigid body constraint. Under the Load section in the model tree, a new load is created, and the type is set to concentrated force. In the Edit Load dialog, the region type is defined as reference point name, and the specific reference selected is reference point 1, which was created earlier and linked to the right edge of the plate. In the Force Components section, the force is applied in the F1 direction, which corresponds to the global x-axis with a value of 40,000 newtons. The other components, F2 and F3, Y and Z directions, are left at 0. The total magnitude is automatically computed as 40,000 newtons. On the model view, we can see the blue arrow originating from the reference point, confirming the correct orientation and application of the load. Clicking OK completes the load definition. This step defines the driving force that causes deformation and stress in the structure, and allows us to observe the mechanical response under this loading condition. In this step 5, run the analysis, we execute the simulation based on all previously defined setup steps, including geometry, mesh, materials, boundary conditions, and loads. To initiate the solver in PrePoMax, the user navigates to the Analyses section in the model tree. By right-clicking on the analysis case, in this example named EX101A, a context menu appears where we have to select Run to start the finite element analysis. This action triggers the solver to begin processing the model using the configured step, constraints, loading, and mesh data. On the right side of the interface, the final visual setup is shown with the fixed edge highlighted in green and the concentrated force at reference point 1 represented by a blue arrow. The solver will now compute the response of the plate to the applied load, producing results such as displacement, stress, and reaction forces. A pop-up window should appear confirming the run is successful. Click Results to go to Next Step. After running the simulation, the final stage in any FEA workflow is post-processing, the process of interpreting and visualizing the results. In this step, we verify the model's equilibrium by checking the reaction forces at the constrained fixed edge of the plate. This step is important to ensure the applied loads are properly balanced by the boundary conditions, confirming the correctness of the model setup. In PrePoMax, reaction forces are reviewed through the History Output section under Results. During pre-processing, a history output request was set for the node set labeled Fixed, and the force component RF1, reaction force in the global X direction, was selected. Upon running the analysis, the output shows that the total reaction force in RF1 is minus 40,000 newtons, which exactly matches the magnitude of the applied load, but with a negative sign, indicating opposite direction. This confirms that the model is in static equilibrium. The load applied at the reference point is completely resisted by the fixed edge. The graphical display reinforces this by showing the highlighted constrained region in red. This kind of verification is essential in finite element analysis to catch mistakes in boundary conditions or load application before proceeding with interpretation of results like stress and strain. In step 6b, displacement, we begin post-processing by evaluating the deformation response of the structure under the applied load. After the analysis has successfully run, go to the Results tab to access the available output data. Under Field Outputs, the user expands the displacement category and selects All, which displays the total displacement magnitude across the entire model. The contour plot shown in the image uses a color scale to represent displacement values, from blue, lowest, to red, highest. This visual feedback provides an intuitive understanding of how the structure deforms. As highlighted in the image, the maximum displacement is reported as 0.4693 millimeters at node ID 2435, located at the free end of the plate near the reference point 1, which is consistent with expectations for a fixed free loading configuration. The color legend on the left side of the plot provides the range of displacements in millimeters. This output is essential for assessing whether the structure remains within acceptable deflection limits and for verifying boundary conditions and load applications. We can also explore directional displacements U1, U2, U3 for deeper insights into how the model moves along each global axis. Continuing with post-processing, we now examine the stress distribution across the model in step 6c, stress. Just like with displacement results, stress results are accessed from the Results tab under Field Outputs. Here we evaluate the internal stress distribution in the structure as a result of the applied load. Under Stress, select Mises, which displays the von Mises stress, a widely used failure criterion for ductile materials. The colored contour plot in the image shows how stress is distributed across the plate, with the scale on the left ranging from 135 megapascals to 1,653 megapascals. The red zone near the loaded edge indicates areas of highest stress. Using the Query tool available under the Tools menu, we can inspect individual nodes or elements to extract exact stress values. As shown in the upper right of the image, the probe identifies node ID 7606 with coordinates, where the von Mises stress is 335 megapascals. This step is crucial in determining whether the structure stays within material limits or if modifications are required. The von Mises stress output allows engineers to assess overall structural integrity, detect stress concentrations, and ensure the design meets strength requirements. In this step 6D, we evaluate how the structure deforms at the material level under loading by reviewing the strain distribution. In PrePoMax, this is done through the Results tab under Field Outputs. By expanding Total Strain section and selecting E11, we visualize the normal strain in the X direction, global axis 1. The contour plot displays how strain varies across the plate, with the color legend indicating positive and negative values. The image shows strain concentrated near the loaded edge, which is expected due to tensile stretching. A strain value of 0.04624 is observed by the probe at node ID 7606, and this matches the region of highest tensile response in the middle of the plate. This result aligns with the theoretical expectation for axial loading on a fixed-free rectangular plate. Understanding strain distribution is crucial for verifying material behavior, calculating elongation, and ensuring the design remains within allowable strain limits to avoid permanent deformation or failure. In the final stage of Exercise 101A, we perform Step 6E, validation, to ensure the accuracy of our FEA model by comparing it with hand-calculated analytical results. This step validates whether the simulation outputs, displacement, strain, and stress are consistent with fundamental mechanical equations. The image summarizes the key parameters of the plate used in the model: a width W of 40 millimeters, a thickness T of 3 millimeters, and a length L of 100 millimeters. The material used has a Young's modulus E of 72,390 megapascals. Under a uniaxial tensile load of 40 kilonewtons, the applied stress is calculated as 333 megapascals using the basic formula. The applied strain is then obtained using Hooke's law, resulting in 0.0046, a dimensionless quantity representing 0.46% elongation. Finally, the maximum elongation of the plate is estimated using the formula, giving 0.4605 millimeters. These theoretical values align very closely with the simulation results from previous steps. The von Mises stress, the strain, and the displacement all fall within a narrow tolerance, validating the model's correctness. This step is critical in both academic and professional engineering analysis workflows. It demonstrates not only that the simulation was executed correctly, but also that the results are physically realistic and consistent with classical theory.